Facebook live audio room over the past few weeks. We've chatted about a number of really interesting tech topics, things like home automation, should you let your kids use tech, Linux, the past, the present, the future. And today's topic is our grand finale, and it is going to be an absolute doozy. I've got two guests here to talk about, is Moore's Law dead? Like, is this the end of CPUs continuing to get faster, at least in the way that we expect them to? And I've got a couple of folks who are extremely qualified to talk about this subject. We've got Sanjay Natarajan, who's the Senior VP in charge of logic development at Intel, and Babak Sabi, who is the Corporate VP in charge of assembly and test tech development from Intel as well. So if anybody knows this stuff, it's going to be these guys. So why don't we kick things right off with just a brief chat about who is Gordon Moore? Like, why do we continue to talk about him all these years later?
Hey, Linus, thanks a lot. This is Sanjay. I'll take that one. Who is Gordon Moore? Boy, sounds like a deep philosophical question. I'm not gonna take it at that level. Let me just talk about Moore's Law a little bit. You know, Gordon Moore was kind of one of the pioneers of microelectronics. He was at Fairchild Semiconductor, and then he was one of the founders of Intel back in the 60s. You know, if you did a word cloud of microelectronics, Moore's Law would be probably the single biggest thing in that word cloud. I think it's quoted somewhere every day in our lives. And if I go back to the beginning, that concept came out of a paper he wrote in 1965. So before I was born, probably before most people on this call were born. And you know, it's a really fascinating paper. If you're kind of a geek about microelectronics, this is one paper I think everyone should read. It's only 4 pages long. It's a quick read. This paper is what all the fuss is about when they say Moore's Law. And it's not a law, by the way. It's not a law of nature. It's not a law of physics. It's not a state or federal law. It's not a law in any way we use the word. It's just an observation. But in this paper, Gordon Moore plotted a few things on a graph, drew a line through it, and said, looks like the number of components on a chip are doubling every year. And that's it. That's the whole, you know, Moore's Law. So a couple years later, he added some more points and he revised that and said, looks like number of components are doubling every year and a half, 18 months. And then a little bit later, with more data in the early 70s, he said number of components are doubling every 2 years. And that was kind of the mic drop final answer moment for that concept. And number of components turned into number of transistors.
Now, let me jump in here. How on earth could he have taken data points that were based on technology that we had literally 50 years ago, you know, 50 plus years ago, and had that continue to be true up until, I guess, you know, sometime maybe mid-noughts, early 2010s?
Yeah, and that's why I say it's not a law. It's not like he, you know, did something to figure it out. I honestly think that, you know, the industry rallied around that as a rallying cry for how fast we ought to be able to go. And so all of the innovation, and you're right, it was about 50 years, and it actually is uncanny how accurate that was for 50 years.
Yeah, that's crazy. I mean, nothing else in technology. We think about anything else that was being predicted 50 years ago. You know, you talk about your flying cars or your escalator sidewalks. I mean, none of that stuff happened.
Yeah. And it's just amazing. And I do think it's the hard work of everybody working in the industry who said, okay, this is the drumbeat. We got to be able to do it at this cadence because Gordon Moore said so. And we're just going to roll up our sleeves and get it done. I mean, it's pretty amazing that he observed this, and then we just took it from there as an industry, that the hundreds of thousands of people working on this said, we're going to, every little bit that has to come together to make this double every 2 years, we're going to go do it.
Now, here's something that I think a lot of people don't really understand, and I'm actually so glad that we have someone from the logic side and someone from the more the physical side of chip development, because a lot of people, I feel like, think that just because you pack more transistors onto a chip, somehow that magically makes it more performant. But that's not true at all, is it?
It's not enough. No, it's part of the story, but it's not the whole story. If you look at what makes a chip more performant, packing more of these transistors, these little switches, is definitely going to give you more performance, because you're going to be able to use that to make more logic. You're going to use that to make more functions that the end user is going to use that'll fit on a single chip. And that's how you deliver functionality and performance to the outside world. The other part of it is making those switches more energy efficient and making each switch go faster. All those three things got to come together.
Now, I'm gonna, man, we've got one of my BFFs over at Intel. Agnes is supervising our chat here. I just gotta say, this is so cool because so she's in PR. She's hopefully here to make sure that nobody does anything they're not supposed to do. But I just wanted to express my appreciation for getting this kind of frank discussion going. When I've tried to do this kind of thing in the past with Intel, it's always been kind of met with, no, we can't just have, you know, these kinds of off the record / casual conversations. Everything's got to go through PR. And I'm really appreciative that you guys are here, because I'm going to ask some questions that I think are, you know, maybe not ones that would have been pre-approved, but that kind of thing. What is the difference? You talk about adding more function to the chip, right? So we get all these additional transistors, but one of our previous topics in these Facebook Live audio rooms was, is x86 dead? And one of the arguments that was being made by one of the folks who's actually at Sci5 and who's really heavily invested in RISC-V, one of the arguments that was made was that a lot of x86's problem is bloat. So what's the difference from your point of view between adding more functions and adding more bloat?
I can probably take that. So, you know, there's one thing here that is really important. That's company to the past. You know, so part of the bloat there that people talk about is that you got to be compatible. You know, Windows 11 comes, different operating system comes, and you got to be able to make it work. So, with the beauty of Moore's law is that, you know, you can handle the bloat, plus add a whole bunch of new functions and capabilities. So you got to keep the size of the bloat, you know, small enough to keep the compatibility, because you don't want to ask anybody, oh, you know, Windows 11 is coming up, you all have to buy a new computer. You can still enjoy using Windows 11 without having to buy a new computer. So I think
now, hold on, I got to jump in, because that is so interesting. And that's something that I think people don't think about today. I think that's something that people take for granted, is back in the early days of computing, a new computer would come out. It would have a completely incompatible architecture, and all the new software would completely break compatibility. I mean, that was fairly commonplace, was it not?
Yeah.
So I guess what I feel like people take for granted these days is that, yeah, you can get a new computer and fundamentally it will be completely compatible with your old software, and vice versa. You can get new software and it'll work with your old computer. But here's the challenge. There has been, you know, the word on the street, you know, whether it's in the press or whether it's even industry insiders, is that Moore's law is dead, right? I mean, I think we've all read the headlines. You guys can't see the video feeds of these guys, but they both have smiles on their faces. It's great, because everyone's heard it, right? So you say that Moore's law has protected us, has protected this backwards compatibility now for decades. But are we running out? Are we running out of runway here? And are we not going to be able to enjoy this kind of compatibility that we have for so long?
So I'll give you my version of it, and Sanjay can give his. You know, I'm sort of like a dinosaur. You know, I've been around in Intel since 1984. Probably many of the people who are on this call aren't even born then. And
not me.
I remember in early 1990, there was a paper from Bell Labs, which, you know, that used to be the big thing, that pretty much said that Moore's law is going to be dead within 10 years max. This is it. And that would have been year 2000. And we are in 2021. So anybody who predicts that Moore's law is going to be dead in 10 years, that means that we just don't know enough yet on how to extend it. Now, Sanjay is in charge of, keeping Moore's Law alive. That's his job in Intel, so he can give you a lot more detail on that.
Yeah, and I'm laughing over here because I certainly don't think Moore's Law is dead. And it's one of those things that literally every year somebody comes out and says Moore's Law is dead. I think, like Babak says, going back to 1990. Rumors of my death are greatly exaggerated. Isn't that the line that somebody used?
Yeah.
And I feel the same way about Moore's Law. I mean, we see a nice line of sight here for the next decade of innovation. We're in the nanometer era in terms of dimensions right now. We're moving into the angstrom era, which is 1 to the minus 10 power minus 10 of a meter. Incredibly small stuff, far smaller than a blood cell or far smaller than the width of your hair on your head. That's the dimensions we're working in right now. And our CEO has said, until the periodic table is exhausted, Moore's Law isn't dead. My addendum, since this is my job, is I will probably be exhausted by then too, and so will my group before we declare the end of Moore's Law. I think we see a pretty rich opportunity set in front of us.
Now, obviously, I said that this was going to be, a very challenging talk, and I'm going to ask the questions that the people want to know the answers to. If Moore's Law is not dead, and if you guys see this sort of this roadmap in front of you, why did Intel struggle so much over the last few years to deliver consumers and especially gamers the kinds of performance improvements that they had come to expect? I mean, I think a certain amount of this is, expectation setting that Intel created for themselves over the years prior to that. I mean, we were getting these, well, not just Intel, whether we're talking about AMD or ATI back in the day or NVIDIA, the way that we were getting performance improvements back to 10, 15, 20 years ago, it was absolutely incredible. And it to the consumer, there's no doubt that it feels like it really slowed down. So how do you reconcile that with you saying that you've got this clear roadmap?
Yeah, so let me go back. Start with, okay, I sympathize and I empathize with the observation, especially in the gaming community. Just a side note, one feature of being in this group used to be that we always make the first chips off a new technology generation here in our fab outside of Portland. We would get in our group some samples of that stuff. So you could have a chip that was sort of pretty healthy, pretty functional, not ready to be sold, but sort of pre-production samples to go use for your own use. And I would go build a new computer every 2 years. So, I'd get a desktop chip with pin grid array. I'd have the fun of going out, setting myself a budget, going over to Newegg and a few other places and buying components and putting the whole thing together myself. And when I had it together, I'd have the fun of playing with bus fractions and monitoring my core temperature and just seeing how much I could cook this thing to get it to go. That was a tremendous amount of fun. I don't get to do that anymore, in part because I don't know how to build laptops, so I can't do much with these chips that we roll out anymore. But I definitely relate to kind of that community somewhat of where you're trying to push performance as hard as you can.
Yeah.
Right. And we have kind of, I would say you're absolutely right to make your observation about the past few years. I think we haven't been up to where we've wanted to be when you look at Intel 10. That's changing. It's already been changing. And, if you look at where we're going in the next several years, we're going to do 5 new nodes in the next 4 years. We've announced a pretty aggressive roadmap to kind of push performance, push power consumption down, push transistors on a chip up. And kind of really regain a performance mantle between now and 2025. I outlined that in a talk back in July, and we've been just marching to it ever since. But we see a pretty positive future for Intel, where we're gonna innovate. We're gonna innovate in the transistor arena. We're gonna go out of FinFETs, which is kind of today's transistor, and into a gate-all-around transistor, what we're calling a ribbon FET. So it's a whole new type of switch that we're going to be putting to use to deliver more energy-efficient computing over the coming years. We're going to do another thing that I think should be really exciting for gamers, which is we're going to do backside power delivery on a chip. What is that?
Tell me about that.
Okay, so your chip, for the most part, is made up of a billion switches or a few billion switches called transistors and miles of wire connecting all that stuff together. And today, all that wire comes to the transistors from the top, and those wires connect the transistors together, and they also deliver power to all of that stuff. We're going to take all the power stuff and flip it to the bottom, and it's going to go to the transistor from the bottom. And there's two things that matter for somebody using this stuff. One is that the voltage drop from this power supply to that transistor is going to get much, much, much less. What we call IR drop, what we call droop, which really matters when you're in turbo mode, what really matters when you're running at high voltage. That's going to get significantly better. So you're going to get a much better experience at high voltage.
So basically on a nano level, you're going to have shorter wires effectively. So
yeah, shorter and fatter, so lower resistance wires.
Got it. So our viewers could kind of think about this kind of like, you know, if they're using a component cable to connect an HD TV back in the day, the longer that cable is, the fuzzier the picture. And this has to do with just degradation of voltages, dropping of voltages, degradation of signaling over longer wires. So you guys are taking all the power side, and you're basically saying, okay, the higher the resistance of the wire, so the longer and skinnier it is, the more this power drops, and the harder it is to balance it throughout this incredibly complex device.
Yeah.
So you make them shorter and fatter. You go in from the back, and boom, cleaner power.
That's right. Cleaner power, better performance at a given power consumption, which is, you know, the name of the game at high voltage.
Right. Okay. And what else?
And, you know, now I've taken all that stuff off the top. So we've freed up the top for better signal routing. So you can have faster wires connecting those switches together. So that's yet another benefit you're going to see in terms of how fast these chips can perform.
So when you say faster, you know, are you talking better logic right now because you've got more space to put logic in now that you're not taking it up with all these power wires? Or are you talking about faster? Like, are we really talking more gigahertz? Are we really going to shatter that 5 gigahertz barrier finally?
Yeah, I'm not going to predict a gigahertz number, but I am talking faster in the sense that the chip should be able to go that much faster. You know, we're really trying to enable better performance at high voltage. We're really trying to speed up those switches so that they can keep up with that kind of clock speed. You know, the clock speed is really driven by how fast these things can switch. They're switching ones and zeros constantly on you, you know, millions of times in a second. And we just want to speed that thing up.
Now, that all sounds amazing. But here's the thing. I published kind of a love letter to Intel about, I guess it was about 1.5 years ago, where I pretty much said, you know, I hate what you guys are doing right now. I hate how you seem like you're stuck in a rut. I love Intel, but I love the Intel that has a fire in its belly. And you talk about how, you know, yeah, you understand our observations as gamers over the last few years, but you're back and you're ready to execute. What happened? You know, why is it new management? I mean, the timing doesn't make sense. I mean, it can't be the CEO change. It's not that simple. Like, it's at least a 3-year cadence on a new architecture. I mean, you guys had to be working on Alder Lake 36 months ago, right? So, you know, what was the wake up call, and why are we getting this renewed vigor now?
Yeah, I'll take my shot at it. Babak can add his. I actually, you know, was at Intel for 22 years, from 93 to 2015. I left in 2015, and I came back about 6 months ago. So, you know, I'm not able to tell you what happened between 2015 and 6 months ago, but I can tell you over the past 6 months that fire in our belly is absolutely here. I mean, we're super passionate about, for example, the two things we just described to you. This is keeping us up at night in a really good way right now. We're really excited to be working on the next big thing in terms of a switch. You know, we were the pioneers of this switch, the FinFET. When we put it in back in 2011, we were the pioneers of that. We were the pioneers of the switch to high K metal gate, which was a huge transformation in how transistors work. So this kind of, you know, geeky innovation is kind of in our DNA. So now we look at innovations like changing the transistor to a completely different architecture. We look at this kind of backside power delivery, which is going to be super exciting when it hits the marketplace. And there's no question that we're back into seeing a sense of excitement around here for innovation like this.
Yeah, I'll add a few things here, Linus. First of all, I want to tell everybody out there that we are back. There is an awful lot of passion inside Intel. Our CEO is a technical geek. When we sat down and talked to him, he wants to talk technical details, and he has really reinvigorated us. There is this massive sense of excitement. There's a lot of new investment, with our, IDM 2.0 strategy, the push to be better and faster. Yeah, I think that, I sympathize with the people out there. We took some wrong turns. We had some, not so good decisions, and that's past. I think we learned a lot from it. I think Sanjay has taken on a huge challenge. He's delivering, 5 new nodes in 4 years. That's just like unprecedented. And there is a lot of investment in us to do better. I mean, one other thing that I add here, looking in the future, is that, Moore's Law is great. Add advanced packaging to it, you're just turbocharging it. Because
Right.
And so I think that, we're going to be able to deliver some really great, exciting products out there in coming years. Just stay tuned.
So I'm really glad that you mentioned that, because I think for a lot of people, the concept of chip stacking or die stacking or 3D 3D chip design is sort of difficult to wrap your brain around. I mean, I think we all kind of fundamentally understand a PCB has a lot of traces routing through it, and then a CPU is kind of like a really, 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 really tiny one of those. But we think of them as kind of this planar thing, this two-dimensional thing. So you talk about some of the new technology that's gonna turbocharge development. For those of you who are just tuning in now, Babak Sabi is in charge of assembly and test tech development at Intel. So why don't you tell us some of the things that you guys are working on right now that are going to make chips better and faster, but that don't rely on Moore's Law to be alive, even if it is still alive?
Yeah, I call it a Moore's Law Plus. That's what packaging does, because we truly believe in Moore's Law and what it can deliver in terms of transistor performance. Now, the role of packaging is really interconnect, right? Because we make all the connections, we bring the wires out to the motherboard, and you make the connection there. And the shorter we can make the length of those interconnects, the better the chips are. It takes less energy, you can go faster. So having that stacking there, that just gives us an ability to have really, really short interconnects. We could put like tons of memory with very, very fast interconnects there, and which is something that we couldn't do before if we were in a planar mode. But with a 3D stacking there, that memory sits underneath the CPU. It feeds the CPU. It's with a really, really high pipe, and this makes it go fast. So I
So
sort of gives you an explanation of the importance of stacking here, in the PC area. And, the other thing that we can add in here is that, as the technologies are becoming more and more specialized, there's some aspects of the technology just doesn't scale the same way. Memory scales differently. Your analog devices scale differently. Now with stacking, you can mix and match different technology for what they're good at. So you could really optimize the overall chip in a way that you couldn't do before. Before, you always had to make compromises. But with stacking and advanced packaging, no compromises.
now tell me something. You talk about shorter interconnects being better, being faster, and you specifically mentioned memory. And I know that as memory speeds have pushed higher and higher and higher, it's become very challenging for motherboard manufacturers to design new, like novel ways to, and obviously a lot of this would be in collaboration with you guys, but to come up with novel ways to connect system memory, at least on the desktop, to maintain that kind of performance, these absolutely insane frequencies that they're running at. So it's been rumored at least a couple of times that Intel wanted to do away with the traditional socketed chip and make the whole platform more integrated. I mean, we've seen a move towards integration, whether we're talking about moving the integrated memory controller on board, moving the PCI Express functionality on die onto the CPU. So do you foresee a future where we are just not going to install memory in our motherboard? Are we just going to have a CPU that has all the memory on board, and you just kind of like what Apple's done with the M1, you have to choose how much memory you have at the time that you buy your system?
Yeah, this is eventually, the question is that where you want to spend the money. You can make the motherboard to be as good as the package. So you can improve that interconnection between the memory and CPU, but then the motherboard becomes awfully expensive. So I think what everybody is going to see is that we are going to bring the memory closer and closer to CPU, control that interconnect, so all the people that the boards don't have to worry about it. So and I think that especially for high-end systems where you want the absolute fastest memory.
Okay. I mean, we've already seen that. I mean, you look at something like the motherboard for a PlayStation 5, right? You've got all those memory dies in kind of like a clover arrangement around the CPU. I mean, is that something that you could foresee on the desktop if it delivered some kind of compelling performance advantage?
Oh, absolutely. Absolutely. We could definitely see that. We can, as long as we know what the distance is, and we can design, the input outputs too. But, people want to have a lot of flexibility in the way they design their motherboard. That's what breaks it. So if we can specify that interconnect exactly how far away the memory should be, what should be the interconnect properties, then you're absolutely right. In Xbox, they control that. There's only one guy who makes it, Microsoft.
Right.
So if we can specify that everybody in industry adopts it, then everybody will get it.
So I guess a question that I have, again, this is very off script, but what does that mean for enthusiasts? What does that mean for gamers? I mean, Sanjay, you were talking earlier about how much fun it was for you as part of your job. I think you said every 2 years you got a budget to go out and really, be immersed in the enthusiast gaming community that you were serving at Intel by going out, picking parts, building your own rig, overclocking it, tuning it. Does this level of integration mean that that's pointless or dead or both?
Well, I'll let Babak speak to the integration side of it because that's packaging. But I will just correct one thing I might have missaid. This wasn't a job. This was a fun thing for me. They gave me a chip. When I said I had a budget, it was a budget that my wife gave me that I was allowed to spend on. This was just my hobby. And I'd like to think I didn't use solder paste the way you posted yesterday, but maybe I did. Maybe, this was all part of a learning experience.
Got it. So, I mean, are we just so close to the razor's edge of what can be done that we just have to accept that things are going to be a little bit more pre-baked and they're going to ship kind of already running as fast as they can go?
There will be more innovation on the system side as well also. So there might be some special motherboards that we can make, for the gaming, in conjunction, with others. So I don't think that this, there will be new interfaces developed over time, new I/O protocols that can allow us to go faster. So I don't think that this is the end. I mean, there is always a limit of how much you can get out of a copper wire. You know, we still can't break the laws of physics, no matter what we do. So eventually there will be a limit that how far we could push the interfaces with copper. And that's when, we'll have to make a move to optical, but we're still far away from that, at least on the gaming side.
Okay, so now one of the things that you mentioned, Sanjay, earlier is that Intel, a lot of the focus is on mobile, right? On laptops. I mean, it's no secret, you're a public company, right? Everyone can look at the product mix and see that laptops are driving a huge part of the business. And so I think it's fair that for quite a while, the gaming community felt like they were kind of an afterthought. We were getting a core design that was really mobile first, energy efficiency first, and, performance second. And yeah, we were getting more of them, and we were getting, better and better iGPUs that were built into these chips. But what the gaming community wanted was, better single-threaded performance. They wanted better, stronger individual cores. Is that something that you feel like you guys are going to be addressing moving forward?
Well, neither Babak nor I are chip architects, so that's probably the exact question you asked is outside our wheelhouse, I would say. But I will tell you, we're committed to being the best of breed for our customers. And we're not just a mobile company. We're not just a server chip company. We're not just a desktop company. We want to deliver the best value and the best product across the board. And that's really our mission is if it computes best with Intel.
Right. So
I want to add that the single thread is a big metric that we're after. Also, the multi-threaded, we saw, with Alder Lake, there's quite a bit of improvement with multi-thread scheduling and so on. So there's a lot of attention paid to all of these metrics in the architecture design.
now, obviously, you guys are a lot more privy to what's going to be happening with Alder Lake than the rest of us are, because I'm not hands-on with chips yet. So I mean, obviously, you guys have talked about it a lot. I'm not gonna poke and prod you for anything that is gonna break the embargo, but it's good to hear that has been a priority. Now, let's steer ourselves back to the main subject of the discussion today. Moore's law. So we've talked about what the priorities are. You guys want to keep making chips faster. Okay, we're gonna have stacking. That's gonna help. We've got additional material innovations. One of the other, very popular headlines over especially the last 10 years has been, never mind Moore's law being dead, but that silicon is dead. Can you guys talk to that? Is silicon dead as a material for continuing to push the envelope in high performance chips?
Yeah, absolutely not. I can tell you unequivocally, I think silicon has a long life ahead of it. As I said, if we believe if it computes best with Intel. So we are kind of constantly doing research in this area. How much can we push silicon? If we need alternatives, what do they look like? And alternatives like 3-5 semiconductors, gallium nitride, silicon carbide, sort of something different from core silicon technology. We've got our fingers in just about every pie right now. But from my point of view, silicon still has a long life ahead of it.
Now, to be clear, these other technologies are in use today. I mean, the Tesla Model 3 apparently uses silicon carbide. So, why would they choose that? And why would you guys stick with silicon?
Yeah, well, they choose it and other people choose it for specific functionality, right? The things like silicon carbide are actively used, for instance, in power applications, because that's a wide bandgap semiconductor. Not to get too wonky with the group, but that's a wide bandgap semiconductor. It can take a very high voltage across it without any breakdown. It's been used for a long time in power electronics. But when you talk about kind of high performance computing, Silicon has been and will be the workhorse for a very long time.
Now, again, let's get a little bit wonky here, because I think that's what people are tuned into this chat for. I mean, these articles about how silicon is dead will often get very, at least very scientific sounding. You know, they'll talk about how there's just these fundamental limits we'll never be able to pass, and we're getting close to them because of the distance between, you know, two silicon atoms. You know, how do you overcome that?
Yeah, and you know, in the end, you can't argue with that. Someday we're going to run out of room, but people have been saying that for, I got to say, 30 years now, that we're out of room. You know, we can't go any below this. And you know, even in the 90s, people were saying there's no more way to do this. The numbers look like this, right? The silicon atom is about 2 nanometers across, 0.2 nanometers, sorry, 2 angstroms across. If you look at where kind of a state-of-the-art technology is, and you look at the transistor gate length, we're running in about 20 nanometers. So, you know, we are running about 100 times bigger than the size of a silicon atom. So we still got a long way to go before we get down to saying, oh, I got to go down. I'm only making this feature with 1 atom. And what do I do when I need to make it smaller? We're a long way from those kinds of dimensions. That's why I say I think there's a lot of life ahead for silicon. And there's a lot of ideas on the table for what to do next.
Got it. Okay. So while we're, I guess, okay, I want to know, what are the ideas for what we can do next? Hit me.
Well, I talked about a couple that we already announced that we're doing, right? We are changing the switch from a FinFET to a gate-all-around. That's a big deal for the industry. And if I get, again, down in the weeds a little bit,
yeah, please do.
Yeah. We used to run a transistor called a planar transistor. We would control the channel. The switch would be on top, and it would control the channel and turn the channel on and off from the top. Then we went to a FinFET, which was, the idea was to control the channel from 2 sides. And you get better what's called electrostatics, which, you know, at the end of the day makes for a better experience at the full chip level. Now we're going to gate all around. We're going to control the channel from all 4 sides. So the gate is going to be all around the channel where current flows through the thing. That's going to provide yet another revolution in how energy efficient these transistors can be. So that's even just what we've talked about so far. Then you look out a little farther, the kinds of stuff we're researching and the industry is researching. Maybe I won't just talk about us in this case, right? The kinds of stuff that the industry is researching is completely different types of switches. We have switches people are researching called tunnel FETs, which are based on a whole different type of physics than what a MOSFET or, you know, what our conventional transistors are based on. You have ideas around stacking at the inside the chip, not at the package level, but even at the chip level, you have ideas around stacking. So we have a lot of innovation going on, you know, that's both physical and materials and electrical architecture ideas, which is why I feel pretty good about, you know, at least the next decade.
Now, stacking is a way for us to pack things in more densely, right? Fundamentally. But here's a question for you. When you have to manufacture multiple layers in a single chip, is that going to drive up costs for consumers in a way that we haven't really seen before?
Yeah, now that's great, because you brought this back full circle to the 1965 Gordon Moore paper, because Gordon Moore's paper was not about performance, it was not about power, it was not really about density, it was all about cost. So if you go back to what he said originally, it was, the main point was that the cost of each of those components was coming down as you got this density improvement. As you put more of them on the chip, the cost per component comes down, and the cost per transistor, in today's kind of modern language, with each new node, the cost per transistor comes down. That, the economics of Moore's law is really one of the important drivers of the whole industry. I mean, this is what the industry is built and banked on, is the economics of functionality getting cheaper with time. We don't see that changing.
Really? Okay, so I mean, talk to me like I'm five. Like let's do it here. If you guys are building a planar, just a two-dimensional chip, right? So my understanding is basically you've got this this process where you're masking off everything that you want to stay, and then effectively burning away everything that you want to go away, right? I
Yep.
mean, on a very basic level, this is kind
Good
of how we build
enough.
a chip.
Yeah.
Okay, so if you have to do more layers of this, doesn't that inherently drive up cost?
It may drive up cost when you talk about it as layers, but when you talk about I'm also packing stuff closer together. So
Mm-hmm.
I'm getting more of transistors in exchange for those more layers. So it's really a fraction you got to work out, right? How many extra transistors are you putting down, and then what are you dividing it by? So the cost per transistor, cost per function is a super important thing to keep track
Yeah,
of.
let me add one more thing here, Linus. So as we can pack more, the area required to uh, realize a function gets smaller. So it's really the area that you take up on silicon that is a big driver on cost. Maybe, you know, now we're going to get real geeky here, but you know, the the cost of making a wafer may go up, but you get more chips on it. So this way, you know, the cost curve is not, you know, it's not going up nearly as much as, you know, from one generation to another. Did
Now,
I explain?
let's talk about costs increasing from one generation to another. I mean, this is a drum that Nvidia is really fond of beating, where they will throw out this kind of big genital measuring number for how much they spent developing, you know, each new architecture. And that number is going up just astronomically as we go from generation to generation. Surely it has to be the same kind of problem for Intel as you guys. I mean, you've had the smartest minds in the world working on this stuff for decades. I mean, getting smarter year after year after year is not exactly easy. So what about the cost to actually develop these new generations of technology? Do we have to absorb that somewhere, right?
Well, yeah, we don't feel the need to talk about any, what did you say, genital measuring numbers. We're pretty confident in what we're doing. I don't think we need to talk about those numbers.
Oh
Um,
no, I don't expect you to give a number. I just mean they often talk about it in those terms, like we spent this much to build it, and it's always higher than the last gen. So it must be similar for you guys, where each time you do a node shrink, or each time you're developing a new architecture, it has to cost more than the last one, doesn't it?
well, like I said, I mean, we're going to let the technology itself do the talking. And I think that's what you're seeing now. And honestly, what you're already seeing and what you're going to continue to see in the innovations we put out, I'm not too concerned about the how much money we have to put in, and I'm not here, interested in kind of standing bragging about any of that stuff and look at how much we spend. That's sort of, that's our inside baseball. What really matters to most people is what are they getting? Like what's in it for them? What capability can we give them for their dollar? And is it worth it?
So here's a question for you, again, from a consumer standpoint. You guys talk about how the cost per transistor is so huge, right? So why is it that from a gamer standpoint, you end up with functions on the chip that you might not necessarily care about? Like I remember going back to, I guess this would be, oh lordy, when was Linfield? That was
Wow.
2009, something like that. Yeah,
Yeah.
it was a hot minute ago. Anyway, back when Intel first moved the GPU onto, I think Clarkdale was when we first got it on package, and then I think it was a generation after that when we got it on die. If the cost per transistor is so huge, why is it that gamers feel like that they can get saddled with functions they don't care about when they would rather have all of that go into the logic that makes their game go faster, CPU logic?
Yeah, Linus, for desktop, that GPU section is fairly small because most gamers want to have, their own external GPU and don't use that. So a lot of it goes to really making the core, the logic stronger, as you said. So they put a small GPU there, you turn on the system, you still don't have added a external GPU or something like that, so you get a bit of functionality there. That's a pretty small area for the GPUs there.
Okay, so do you think it's because I know you guys recently, this is in the last couple of years, started shipping desktop processors that have those GPU units fused off. So that I believe it's the I can't remember what the suffix is for that particular lineup off the top of my head. But do you think it is possible that we could see a pure CPU come back?
I that's not my field here. I don't make those decisions. So I can't answer you that question.
I actually I kind of love where you're going with that. So you guys have so many moving parts, right? Like ultimately it's someone's team's job to take the vision for what the next product is going to be and execute it. So has the vision changed under the new leadership lately?
I think the tagline for the vision is this IDM 2.0, and that, Pat Gelsinger rolled that out when he came back, and he left also like I did. He was here a lot longer than me, and he came back, and he came back with a strong vision. One aspect of it, which I got to tell you, I absolutely love, is bringing the geek back to Intel. Like I'm really relishing this period that we're in right now, where we are all about technology. It's a lot of what we talk about. We have these, what I say, wonky discussions a lot now. It's not just talking about management and business. It's a lot of talking about technology. But IDM 2.0 is this idea that we're going to have our core of we design our chips in-house and we manufacture them on our technology, the best technology we can make. We have some group of products which will go outside for technology manufacturing. They won't be made in-house. Where it makes sense, we'll take them outside. Then we got the third piece of it is bringing outside designs in and taking advantage of our performance leading technology and manufacturing them in-house. Stuff that is out the outside, and we've talked about engagements with Qualcomm and Amazon. We haven't talked about anything else, and I won't do that here. But those are two we've mentioned in the past as the idea of this third leg of the stool of IDM 2.0. So that's the vision he's laid out for us. And when it comes to my side of the business, it's not really to worry too much about how designers are using all those transistors. It's really to make the best transistors and the best wires on the chip and putting it all together.
Now, tell me something. Do you feel like bringing on this outside business, I mean, honestly, as just a tech dude, it was baffling to me that for so many years, Intel kind of kept all of its manufacturing expertise limited to its own devices. I would look around myself in the world and I would go, boy, this thing could be so much more power efficient, or this other thing could be so much more performant if Intel just, instead of building 2 fabs, built 8 fabs and manufactured for other companies. Do you feel like this new idea of bringing in third parties' products, third-party IP and manufacturing it is going to help you do your job better? Is that going to give you more resources to build better transistors?
I think if I just speak to my business, the process development, it definitely helps us. It gives us more insight into what everybody needs. Like it really gives us a broad understanding of different types of products, what they need, how they can benefit from what we have today, and how we can make what we have today better to make those products better. So, to me, it's kind of a virtuous cycle now. that we've really opened up our exposure to this outside, foundry ecosystem, fabless ecosystem to bring that in.
Do you feel like it's turning Intel into a more collaborative player?
Yeah, let me add that here. This connection to the outside world, some of these people are even our competitors, but that's okay. Getting all of these inputs from different point of views from different companies, it's just going to help us to come up with better technologies, better silicon, better packaging, how to put all of these things together better. So I think, this thing that, Pat started is amazing. I mean, it's only been just about 6 months since they announced it, and I think the input has just been amazingly great. So
and
yeah.
I'll toot the horn for Babak's team, because they've got some pretty amazing packaging solutions like Foveros Omni and Foveros Direct that give you kind of ultimate flexibility. Now you can take die that we designed and manufactured in-house, combine it with die that we designed and manufactured it elsewhere, even potentially combine it with that third piece, die designed by somebody else, manufactured in-house. The packaging technology really gives you like incredible mix and match capability.
I just got to do this. So, Linus, if you let me just brag for a second, I don't know how much you know about Ponte Vecchio, which is this big graphics chip that we just talked about. It's an absolute monster. It has 104 slices of silicon in it. It comes from 4 different, kind of silicon technologies. It's all packaged in one place. It's all put together using various assembly technology, assembling it together. This is sort of a showcase of what can be done.
So why is having such a big chip beneficial?
Oh,
Let's explain it for the listeners here.
I mean, the computing capacity that you get out of this chip is just absolutely amazing. And the reason that you want to pack in so much in one place there is again, it goes back to the interconnect. It depends on the workload that you have. Some workloads require a big chunk of continuous computing section together, and you can't have it in 2 separate packages that you put side by side. The same issue that you talked about, memory being too far away from the CPU, and it's got. This is, you put it all together in one package. You could do stuff with some workloads that require that, computing capacity, and just do it in one package that you couldn't do otherwise. That's why it's so important to put so much in one package.
So, I mean, yeah, explain it like we're all 5. I mean, why can't you? I mean, it's not like Intel hasn't been building, multi CPU platforms for many years now, right? So why can't we just take 2 of these and put them together on a motherboard? What are the physical limitations? What happens?
We have done that before, putting 2 CPUs together in one package. We did this in 2000. So becomes a question of economics and cost, and also, so that's one reason. The other reason is that what is it that you're trying to do? There is a workload that you're trying to optimize it with, right? If you put too much there that is well beyond what's needed there, then you're wasting it, and people are not going to pay for it. So we got to really optimize, the computing capacity with the workload requirement that we have.
Okay, I want just a couple more questions from you guys, and I'd like each of you to kind of hit me in turn. And I want to hear what is sort of the, like, man, it excites me so much to hear that you guys are getting your geek back on over there, because it was, again, back to my kind of love letter to Intel. I love you guys when you're being you guys. I don't love you when you're being an accounting company. An anecdote that really broke my heart was I was talking to a gaming influencer who was asked to come in and speak to executives at the VP level. And this is back a number of years ago now, so it's in the past. Let's move forward. But basically, he was asked to come and speak about game streaming, like Twitch TV, stuff like that, and gaming, and why it matters. Just talk about it, give kind of an explanation of that culture. And at some point, midway through the presentation, one of the people in attendance put up their hand and kind of went, okay, so you're saying that like these faster, like if we build faster like chips of this sort, that makes it better for the game streaming. And he's kind of standing there awestruck. How could you ask something like that? You must be just a business person first and a technologist second. And so it's so exciting for me to hear that that's dead. I'm glad, but I want to hear from each of you in turn. What is the most fun, geeky, passionate conversation you've had around the water cooler in the last 6 months, right? Like since Pat returned and you guys have gotten this fire back in the belly. What excites you to work on, or what have you heard from your team? Like
So I'll give you one example, and which really, there was a project, and it's going to require a lot of investment for me to go work on. So we had a review, with my boss and Pat, and explained what it is that we want to do, how we're going to get it done. Why so good? And he listened. He sat there, listened intently, and I said it's going to be ready by this time. He said, "I love it, but I want it 2 years faster." It was like, oh, I like this kind of challenge. So
that's fantastic.
That's the kind of environment that he creates. It's like, I can see the potential in what you're saying, but I want it yesterday, which is.
That's so much better than I can see the potential in what you're saying, but I want it at half the cost.
Yeah.
Yeah.
Oh, I'm so glad to hear that. It's going to be hard to top, Sanjay. You got anything for me?
I do. Well, I have my own episodes with Pat where he says, great, pull it in. I want it faster. I got enough of those. But I tell you, there's a number of innovations we're working on that keep us around the water cooler lately. But this backside power delivery is a good example of one where, we kind of think this is going to be revolutionary, in a way that the industry hasn't seen revolutionary in a long time. We think it's going to have really change the way people can get value out of their chip and ultimately value out of their computers. And honestly, we are geeking out about the mechanics of making this kind of backside power delivery. It's difficult. I should probably let you know. If it was easy, we would have done it by now. If it was easy, everyone else would have done it by now. It's not easy, but we actually feel super confident that we know how to do it. That's the kind of mojo that's back right now, is just the confidence in our ability to execute on technology ideas.
Well, that's really exciting. It's very clear from talking to both of you that you do not feel like Moore's Law is dead. But I think what we also learned as part of this conversation is that Moore's Law isn't really the thing that I think a lot of consumers think it is. A lot of people think it's going to get faster. It's going to double in speed every 2 years. But really, it's an economic law. It's that the cost is going to go down, and this technology is going to get more attainable, more accessible for more people on this predictable cadence. And it sounds like whether you're able to keep shrinking the transistors, whether you're redesigning the transistors, whether you're finding different ways to pile them up on top of each other and make a leaning tower of transistor, or power it from the back, or whatever else, there's plenty on the roadmap. And I, for one, since I have you guys here and I don't get these opportunities very often, I just want to say, hey, don't forget about the gamers. Don't forget about the overclockers. We may not be the biggest business segment compared to mobile or compared to data center, but we definitely love you guys the most.
Yeah, and if it helps you any, Linus, I do my own overclocking, so no one's gonna have to explain this stuff to me. I know what you're talking about.
All right, good stuff.
So
Thanks a lot.
thank you.
Yeah, thanks a lot for coming on. If you guys are looking for something else to check out from our Facebook Live Audio Room series, we've got a ton of great ones. One of my personal favorites was Linux Past, Present, and Future. That was with Wendell from Level 1 Techs. And if you guys are just tuning in now, you're going to be able to find the entirety of this chat at the top of our Facebook page. We're going to have it pinned there. Sanjay, Babak, you guys are not really public figures in the same sense that a lot of our other guests have been. Can you, is there anywhere that our viewers, or excuse listeners, I'm so used to saying viewers, this is Audio Room. Is there anywhere that our listeners can go to kind of follow what you guys are doing, what your teams are working on? Do you have a blog you post to? Are you on Twitter? What do you guys, are you guys accessible?
Yeah, you can find me on LinkedIn. You can find me on Twitter. You can find videos of me talking on YouTube. It's all out there. You know.
All right. Oh, sorry, Babak. Your phone's a little far away from your mouth. Try one more time.
I'm on LinkedIn too, and you know I get a lot of questions there. So people, I ask everyone, feel free to contact me there, and
all right. Oh man, that's such a foreign concept to me. Yes, my social network is LinkedIn, but that's totally a thing that I just don't even think about. All right, thank you so much, you guys, for making the time for this, and thanks so much for just having such a frank discussion. I think this has been really insightful, and I'm excited. So
thanks,
if that
Linus.
was the objective, to get
Good to
people
talk to you.
excited, then
Yeah,
great job.
Thank you.
Bye.
All right, thank you.
Bye, everyone.